Okay, chapter 3. We're going to start. It almost seems as though we're shifting gears here a little bit, but we are going to probability. And a lot of statistics is based off of probability, obviously, because the root of that word is what's probably going to happen. That's where probability comes from. For example, we did that one with the number cube the other day, and I gave you different information, and when I gave you different information, your probability changed greatly. Okay? And so you got to watch out. You have to understand that information is very important. But a probability experiment, you can probably kind of figure out what that is. It's some kind of action through which specific results, maybe it's a count or some kind of measurement, or if it's a survey, maybe responses. You know, how do you get them? How do you obtain this result? Perhaps, you know, an experiment could be flipping a coin 20 times. Would that give you information? Yeah, that would give you counts, right? How many heads, how many tails? Or maybe it is a survey. You know, how many said yes, how many said no, or how many said that, what was it yesterday, pizza was their favorite food. Isn't that what we said, right? Or some kind of measurement. Maybe it's somewhat like, don't like, you know, stuff like that. Okay. So what would you consider an outcome then? Just an outcome, maybe if I say it that way. In this case, maybe a response, right? Or when I'm flipping the coin, maybe getting a head, or you know, something like that. It's basically, so if you want to narrow down the definition, it's just the result of a single trial. Who knows what it is? Maybe it is a question on a survey. Maybe it's a roll of the die, flip of the coin, something like that. It's just a result of a single trial. Okay. Sample space is actually something I've said a few times already. I kind of guess I assumed you knew what that was. But a sample space is basically all the possibilities, all the possible outcomes of an experiment. So for example, if we were to say, let's say I told you to flip a coin twice, and I told each one of you to flip a coin twice. Well, there are options there, right, of what can happen as far as heads and tails, right? Obviously, the sample space in that one would be you could get a head and then head, right? That's a possibility. Do you agree with that? Or you could get a head and then a tail, right? Or you could get tail and tail, yep. Or you could get tail and head. Okay. Do you agree that's the sample space for this particular, if I said flipping a coin twice? Right? That's what can happen. And in this case, do you agree that they're all probably the same amount of likely to happen in this case? Okay. When you make a sample space, that's a lot of times what you're going to want to try and do, make sure that they are all equally as likely. It makes life a lot easier when you're doing probabilities. Okay. So in this case, an event, well, I've just given you different events right there, right? An event is some kind of subset of the sample space. And it could have one or more of the outcomes. You know, I could tell you that event, I could call it event A if I wanted to. So I could say event A would be that the first time you did it, you got head, head, and the second time you got it, you got tail, tail. Do you see what I mean by one or more? I could make an event mean one or more of the outcomes. I can make it all the outcomes. Then you know the probability of, you know, of that particular event. But a subset of the sample space. So it could have just been, you know, and maybe event B is all that happened is I had you do it once, and event B you got head, tail. Okay, that's an event. Okay, it could be one or more. So keep that in mind. So do you see how that differs from an outcome? An event and an outcome. Do you see how they are different? That's key. Okay. A simple event. Just one outcome. So of the two above, is event A or event B a simple event? Yeah, one thing happened, right? It wasn't two things. It's a head, and you know, you're thinking, well, it's a head and a tail. Yeah, but that outcome was just one possibility, right? Does that make sense? I'm saying that? Okay. Did I give you? Oh yeah, I spaced yours out a little bit more, right? Okay, good. Mine are all right next to each other because I typed them in. So any questions on these? I think I've given you some examples of each one to try and help you out, right? Yeah. Right, exactly. Just one trial. Like for example, an outcome here could have been that I had heads, tails. Okay, where an event could be any subset of that sample space. Like any of these, I could combine 3 of them, or I could combine 2 of them, or that's where we're talking more about events. Okay. So what do you think here? And here's where they kind of forgot some stuff here. So decide whether the event is simple or not. Let's say selecting a computer chip from a batch that has been manufactured that day. Kind of forgot some information there. So here we go. Event A, we'll say, is selecting a specific defective chip. And probably the easiest way to determine if it's simple or not is to try and tell yourself, because up there we said that it has a single outcome. And if I'm looking for a specific defective chip, how many outcomes are there? Is there only one outcome if I'm looking for a specific one? What if I take out the word specific? If I'm just looking for a defective chip, assuming there's more than one, is that a single event, or could I get that result many different ways? I could, right? There's many different ways I could work. And so that wouldn't be a single outcome. But here, seeing it says a specific defective chip, this is a simple event, according to the definition. Because there is the one outcome. I pick that one chip that I want. Is it very likely? No, but that's not what we're asking here. We're asking, is it a simple event or not? One way maybe to look at that is think of simple versus complex. You know, complex event, you would think is more stuff's happening, more possibilities, right? How about rolling at least a 4 on a 6-sided die? So we'll say that event B is actually rolling at least a 4. Well, how many outcomes are there? So here the outcome is getting that chip, right? So here, down here, the outcome or outcomes could be 4, 5, or 6. Do you agree with that? So is there more than one outcome? Yeah. So that is not simple. So that's really the distinction between simple and not. So any questions so far? No? This is probably the one you're most familiar with. Sometimes called theoretical and sometimes called classical probability. Okay, this is the one you are most familiar with. And you can again paraphrase once we talk about it. You'll use this when each outcome in a sample space is equally likely to occur, and again, that's what you want. Let's take a rolling a die. Is each outcome equally likely to happen? It is, right? 1/6, right? And so that's kind of the sample space that you're looking for. The classical probability for an event E is given by, and I have a little formula that'll be coming up next. And notice how we write that, P and then in parentheses E, that means probability of event E, right? Normally you'll specify what that event is. So it's the number of outcomes in that particular event and the total number of outcomes in the sample space. So could you apply that to the rolling of the die? Yeah. If event E is rolling a 4, well, how many outcomes are in event E? Well, 1, you roll a 4. There's only 1, right? So there's 1 in event E. There's 1 possibility. How many are in the sample space? You could roll a 1, a 2, a 3, a 4, or a 5, or a 6. 6, right? So you see, this is kind of like how I used to do it before, successes over total. Very similar to the way you've probably heard it before. This is much more specific. Or here, if I said you flip a coin once and you want to get ahead. Well, how many outcomes are in event E? If that's event E, then I'm just saying just one flip. Flipping ahead, how many ways can you do that? Well, one. And then total number of outcomes in the sample space, well, it's either heads or tails. So you agree it's 1 over 2? Okay. So you see what I mean? This is kind of the probability that you've been doing since you started probability. Okay. So I think a lot of times it is helpful to actually, if we're talking about a 6-sided number cube, sometimes it is helpful to actually write out the sample space, and I kind of maybe think you should get into that habit, especially if it's a small one. So the sample space, seeing it's a new word for some of you, again, is basically a list of all the possible outcomes. So, agreed? Now, what if I said we were rolling 2 die? Does that change your sample space? And I wanted you to add them together? Well, yeah, that changes your sample space a lot. But here we're just saying you're just rolling just one. Determine the probability of the following events. Event A is rolling a 3. So how many ways can I roll a 3? 1. Okay, so we know that the top, so we'll say the probability of A, because this is event A, is equal to, well, your numerator is 1, right? Because that's how many ways that event can happen, right? And rolling a 3, well, is 1, and then how many are in the sample space? 6. Again, we knew that, but you tell we're looking at it in a different way now. We knew that. We know this next answer, too. Well, at least I hope we know this next answer. Probability of rolling a 7. How many ways can you roll a 7? None, right? Let's face it, this isn't even in the sample space. So how is it possible? It's not. So how many ways can you do it? You can't. Is there still 6 in the sample space? Yes. But what are the chances of rolling a 7 with 1 die? Yeah, 0. And of course, all probabilities range from 0 to 1 in decimal form, right? Or 0% to 100% in, yep, okay. If you do percentages, right? 100% as a decimal is 1. Okay, so 0 to 1. So, whoa, event C, this is different. Rolling a number less than 5. So, how many outcomes are there? 4. So let's just talk about those outcomes. I could roll a 1, I could roll a 2, a 3, and a 4. Again, if you want me to talk success, does that make what I wanted to have? That's kind of what I want to have happen, right? I want one of those 4 to happen. So that's all the outcomes in event C, right? And so there's how many? Well, there's 4. Because they're all equally likely, right? So that's why this works. If they weren't equally likely, then we'd have a problem here. And how many in the sample space? Well, it's still 6. In other words, 2 thirds. Which is again between 0 and 1. Or if I did this trial 3 times, I would expect to be successful. If I did it 3 times, I would expect to be successful twice. Okay? If I did event B 6 times, I would expect to be successful none. And if I did the for event A 6 times, I would expect to be successful once. Any questions? All right, statistical, sometimes called empirical probability. It's based on observations from a probability experiment. And again, I'll give you a little formula like that. It's very similar, but we'll make some distinctions as we go. So the probability of that event E is the frequency of the event. Because if this is an observation, it's just, well, how many times did you observe event E happening? So the frequency of it divided by the total frequency. Have we done that before? Yeah, I think we've done that F over N thing that I have on the end there too. Yeah, what is this called? You actually had to do it for your, yeah, say it. Say it. Relative frequency. Very good. That's exactly what it is. And you might wonder, well, how is this different? Well, let's face it, when we have a die, we know there's 6 outcomes, we know that. That's theoretical. But sometimes stuff is based off of just observations like this next one. An insurance company determines that in every 100 claims, 4 are fraudulent, meaning, not real. Okay, the people just wanted the money, all right? Or they just went out to their car, tried to hit it with a baseball bat a bunch of times, and said it was hail damage. What is the probability that the next claim the company processes is fraudulent then? This is definitely more of your, again, statistical or empirical, because obviously where did this insurance company get their information from? They did their claims, they made some observations, hey, overall, every 100 claims I get 4, right? So what is that probability then? Well, that the next one, well, it's still 4 out of 100, but we're not going to write it that way. 1 out of 25. Just heard somebody mumbling a lot. Or 0.04 if you want to write it as a decimal. So is it very probable? Not very probable, no, because the closer you get to 0, the less probable it is, and the closer you get to 1, the greater the probability. Okay. So do you see the difference between that and the previous example, how the probabilities are kind of figured out a little bit differently? And there's one more type, subjective. We're not going to deal with that one a whole lot. Yeah, results from intuition, educated guess, or some kind of estimate. I guess a good example of that would be, you always hear the doctors, well, they're trying to get away from this now, but doctors say, oh, you have a 90% chance of surviving. Or do they just memorize all this stuff? I don't think so. That's just, would you say that's an educated guess? Yeah, 90% chance of survival. That's better than saying 10% chance of dying, right? So that'd be a good example of that one, because obviously that was some kind of intuition or educated guess. Everybody good? All right, classify each as classical, empirical, or subjective. Again, if you interchange the words, it's fine. So this first one here says the probability of your phone ringing during dinner is 0.5. Well, how do you think somebody would come up with that? Do you think people sit there and tally this up? That's, wouldn't you say that's kind of just a guess? They say, it's a 50-50 shot. And maybe that, if you think more theoretical, that's probably either it does or it doesn't. There's 2 options. Are they equally as likely? Well, probably not. So that's where it gets away from that. I would say that's definitely subjective, because you're not going to sit there and tally it every night. All right? And if you do, maybe you should find some other hobbies. Number 2, the probability that a voter chosen at random will vote Republican is 0.45. Again, you got to think, how did they probably come up with this information? Okay, how would somebody more than likely get that? Yeah, or based on some kind of phone survey or something like that. So did they look at something to come up with that number? Probably. So they made some kind of observation. So that's more empirical. And here's probably, I'm hoping on number 3 that you understand where the typo is. Well, actually, there's 2 places it could be. But the probability of winning a 100-ticket raffle with 1 ticket is 1 out of 1,000. So we need to change one of these 2 numbers. And I think we'll just change this one and say it's a 1,000-ticket raffle. So, yeah, that's it. That's what you've done since you started probability, right? I mean, that's just how you look at things. What's the sample space? Well, each of the 1,000 tickets, right? And if they're each, do you agree that they should each be equally likely to win? Yeah, that's the probability we've been doing, and we'll primarily focus on this entire year. But it's good to know that there's other possibilities out there. Law of large numbers. Do you agree with that statement? Can you give me a good example of how that could hold true? Okay, kind of. I was thinking more along the lines of flipping a quarter. Do you agree it should be 50-50 relatively? But obviously, let's say if we all did it, is it possible that we could all get heads? It's way more possible that that would happen than if we had everybody in the school flip the coin and they all got heads. Do you agree the more people we have do this, the more it's going to get towards what we expect it to be based on our knowledge, which is more theoretical and classical? You agree with that? And so that's why when they do surveys and stuff, they try and get enough people in there so that it would actually, hopefully, tend towards that theoretical or classical. Okay, I hope you agree with that. Okay. But obviously there is a chance that two of us would do it and one would get heads and one would get tails. And that is a possibility, but overall the large numbers the better. The complement of event E will be notated as E prime. You can write all that down if you want. That's the technical definition. But let's basically say if you have, let's see, I put an example here. Let's say you have the probability of being successful, let's say being successful at something, I don't know what, is 0.765. Maybe that's the probability of, actually that's pretty close to the number of newborns that survive in the first year. Pretty close. And so if that's successful, the complement of that in this case would be, well, not successful, right? So the easiest way to look at this complement is basically just 1 minus E, isn't it? 1 minus whatever, well, probability of E, sorry, would give you the complement. And in this case, basically you just have to take 1 minus that, and we get the unfortunate probability that, you know, the child does not make it. And actually, it's a little low, isn't it? Yeah, a little high for probability of not making it. Is, well, you take 1 minus that, and what do you get? Do you agree with 0.235? So complement is quite easy. Okay. Okay. Any questions on anything we talked about today? I know it's kind of weird thinking of the subjective and the empirical, right? But theoretical is much better. The one that we're used to. Anything else?